Alright, so very good evening and welcome back to these sessions where we'll continue discussing all the principles that we've been learning. So today let's complete our discussion on the principles of sampling, right. So we have begun discussing the principles of sampling in the previous session, right. So I've given you this problem, right. I said you have just one sinusoid, right, and if I sample the sinusoid, I get all these sinusoids which give you the same samples at the same point. 2 pi by t times ts times k plus minus omega naught times t plus minus phi naught. Now let's get a feeling, this seems very abstract, right. So let's get a feeling of some numbers here, right. So the angular frequencies are 2 pi by ts times a plus minus omega naught. So the Hertz frequency, cycles per second, or Hertz frequencies are divided by 2 pi. So 1 by ts times k plus minus omega naught by 2 pi. So this, we can write as. Now what is 1 by ts? 1 by ts is the sampling frequency. And what is omega naught by 2 pi? Omega naught by 2 pi is the original frequency at which you are sampling, original sinusoidal frequency. Let's take concrete examples. Let's take f0 to be 1 kilohertz, okay, and let's take 1 by ts, which is the sampling frequency, which we'll call fs, to be 20 kilohertz, okay. So what frequencies, can you list the frequencies? Let's do that. Let's do some exercise, at least where we work in groups now, right. So list the frequencies that we are talking about. And I'd like one of you to come and solve this. So we'll take this like a session where you work out problems with me. Yeah. List the frequency that we're talking about here. Remember, k takes all the integer values, right? Yeah, yes. Well, I'm talking about those frequencies. All these frequencies which produce the same samples at the same points with the proper phase. Yes, so we want to list these frequencies, the Hertz frequencies, right. So I've listed the Hertz frequency f0 and the frequency 1 by ts. So based on that, I wish to list these different frequencies whose samples could produce the same, the sinusoids of these frequencies would produce the same samples at the same points, which means, why am I trying to do that? Let's understand. You took a sine wave, right? So you took the sine wave, you took a sinusoid, right? And you sampled it, meaning you reduced the sinusoid to very narrow pulses, right? So you reduce the sinusoid to very narrow pulses. And you were asking, are there any other sinusoids which will give you the same samples, the same points? Why are we doing this? Because we want to find out what is the ambiguity created, what is the confusion created by sampling, right? Now let's take a minute first to appreciate why we are doing this. We are doing this because we want to identify, see, once you have sampled a signal, the problem is not that you cannot reconstruct some signal from those samples. The problem is there are just too many of them, right. So, now first appreciate the problem that is created by sampling. When you sample a signal, you get several samples and you ask, can I reconstruct the signal from its samples? The problem is with the signal. When you say the signal, that's where the problem lies. You can very easily reconstruct a signal from the samples because there are a million ways of interpolating between the samples. There is no problem. You can always reconstruct a continuous time signal from the samples. The problem is, if there is a particular signal which has been sampled to get those samples, how unique is that signal? That is what we are trying to understand with this example. Are you now understand? So, when you convey this in a class, when you talk about sampling in a class, your difficulty is not that you cannot reconstruct some signal from the samples. Your difficulty is there are just too many of them, which one do I choose? Now, we are illustrating this idea with a simple sinusoid. We are saying I have one sine wave, I have sampled this at many points, right, spaced by 1 by Ts like this, right. How many such sinusoids could I have reconstructed which have the same samples? That means, if I look at the points of sampling, can I at all distinguish between these sinusoids? That is the question, right. Now, at the points of sampling, we saw that we cannot distinguish, right, because you know that if I substitute T in all these frequencies, if I substitute T equal to NTS, we get the same samples. At all points T equal to NTS. There is no way to distinguish, which means that even if I tell you that I had sampled a sine wave to get those samples at those points, there is not one but an infinity of sine waves which could have given you those samples at those points. I had also asked you one more question. Suppose I add all these sinusoids with the same amplitude and with the phase as I had specified. How do you specify the phase? If I take plus omega naught here, I should use the phase plus phi naught there. If I take minus omega naught here, I should use the phase minus phi naught there. Now, so this is these two questions we had asked, isn't it? Now, I first want to answer the question, which are these frequencies? So, I have taken an example. I said, suppose you began by sampling a 1 kilohertz sinusoid, right? And your sampling rate was 20 kilohertz. So, what frequencies are we talking about which give you the same samples at the same points? Now, please list them, tell me. Yes, let's list them. Let's begin with 1, right? For k equal to 0, you have 1, right? What is the next one? 9 and 12. Oh, sorry, yeah, 19, yeah, 19 and 21, yes, then 39 and 41, that's correct. 59 and 61 and so on, isn't it? Right? And this can go on forever. That means you have an infinity of, a countable infinity of frequencies, sinusoidal frequencies, all of which would have resulted in the same samples at the same points. So, this tells you about the ambiguity created by sampling. What is the uncertainty that sampling creates, which you have to now resolve? Now, how can I resolve the uncertainty? I can tell you that the lowest frequency component from among these is the frequency component the frequency that I had used, the lowest of these frequencies. Then, of course, the answer is clear, right? But now let's take a different example. Suppose I had f naught equal to, now this is one example, right? Let's take a separate example. Let's take f naught equal to 11 kilohertz and let's keep Fs equal to 20 kilohertz. Now tell me, now list the frequencies and tell me which frequencies would appear. Start listing them. Of course, 11 would appear, yes. What are the next possibilities? When k is equal to 1. Yes, 9. Take one at a time. So 9 and 31, that's correct. Then so you have 40 minus 11, is that right? 29. Yes, then 51, is that right? Yeah. Yes, so 49 and 71, and this can continue. Is that right? Now, if I use the same criterion, take the lowest of the frequencies, will it give you the correct frequency? No. That is where aliasing comes. So, now this 9 kilohertz frequency, which was not what you used in the first place, is also a possibility. You see that? Yes? Yeah, I shall repeat again. So, you see, in this case, these were the frequencies that were created. If I use the criterion, now I have to choose between them, isn't it? Suppose I base my choice on this criterion. Take the lowest of the frequencies which are possible. Then the choice is very straightforward. It was the 1 kilohertz frequency. But in this case, which are the frequencies created? 11, 9, 31, 29, 51, so on and so forth, right? Which is the lowest of these frequencies? 9. Is that the frequency which you had sampled in the first place? No. What had you sampled? You had sampled an 11 kilohertz frequency. So the 11 kilohertz frequency starts behaving like a 9 kilohertz, or rather, the 9 kilohertz frequency pretends to be the 11 kilohertz frequency, right? So it's, in fact, that's what, see, what does the word alias mean? What is the, the meaning of the word alias in common parlance or in common conversation? Yes? Look alike, not quite look alike, it's name alike. Yeah, posing. Yeah. So alias really means acquiring a different identity, a false identity. So you see, so this is a very simple way to bring out the idea of aliasing. You have this frequency which you had sampled, but then there is, if you use the criterion of the lowest possible frequency which could have resulted in those samples at those points, it is something different, right? And that's where the problem arises. In fact, now if you say something else, suppose you say that I want to accept, suppose you had some idea that your frequency could be up to 12 kilohertz, right? And you said, well, I'll keep all the frequencies up to 12 kilohertz, which would result in the same samples at the same points, right? How many frequencies would result then? You have the 9 kilohertz frequency and the 11 kilohertz frequency. So in place of one frequency now, I'm getting two frequencies. So that create beats. In fact, then it would become, if you take a 9 kilohertz frequency and an 11 kilohertz frequency of the same amplitude, it will become an amplitude modulated pattern whose carrier frequency is the average. That's 11 plus 9 by 2, 10 kilohertz. And it looks like two side bands of 1 kilohertz each. Is that right? So, this is where the problem of sampling comes, right? Now, what is the criterion? As you see, in fact, even if you take this very simple example, you can justify or at least appreciate the Nyquist sampling principle. Many of you had stated the Nyquist sampling theorem very correctly. You had said that you must sample the signal at least twice the maximum frequency component. Can we quickly see it from here? Can we quickly see? Let's begin with this expression. You have the frequency f naught, right, which is omega naught by 2 pi. Now, which is the next frequency created according to this as an expression? It is for k equal to 1. What is that? So, you denote 1 by Ts as Fs, right. So, what is the next pair of frequencies created? Fs minus F naught, Fs plus F naught. After that, what are the next frequencies? 2Fs minus F naught, 2Fs plus F naught, and this can continue, right. Which among these frequencies is the lowest, right, which can cause a problem? Fs minus F naught, is that right? So, if Fs minus F naught is greater than F naught, a problem will not be created, is that right? And therefore, Fs needs to be greater than twice F naught. Can you see that? Now, while this is not a formal proof of the Nyquist sampling theorem, it illustrates the idea crisply and clearly. Just beginning with one sinusoid, right? And we can take this idea further. We can ask, what happens when we add all the frequencies? Now, I am going to leave that as a question for you to think about, right? And my teaching associates might help you solve that problem later. The problem is, take this sum. This, you will solve it later. So, you take it with you and solve it in one of the classes in which you will be doing with my teaching associates. So, the exercises, or rather I would, in fact, one thing I love doing, and my own students would remember this, that I love giving challenge problems in the class, and this is one of the challenge problems. Problems are slightly difficult, not just tutorial material, not just routine tutorial material. So, I am going to give you a challenge problem too, and this would be one of the things that you will do as an exercise in one of the sessions. TAs can note this, right? So, you can take this. The challenge is, find the partial sums summation. So, the first frequency, take the frequency, the original sinusoid, and then k equal to 1 to n, right? This. So, A naught cos plus the original frequency. Yeah. Now, please understand the question. What I am asking you to do is, you have the original sinusoid and you have all these sinusoids which are created, which have the same samples at the same points, right? When you add them, you must add both so this summation has two terms actually in the summation. The plus term taking plus with both, and the minus term taking minus with both. So, in the summation inside there are two terms, right? The frequency, which is Fs or k times Fs plus F naught, and with the phase of plus phi naught, and the frequency k times Fs minus F naught, but with the phase minus phi naught. So, the challenge problem for you, or the exercise which you should do in one of the sessions with the help of my teaching associates, is to find the partial sums. That means, sum this up to n terms, and if possible also try and use any open source software, mathematical software, to sketch this sum, sketch the sum, right. So, you can sketch the sum for n equal to 10, n equal to 15, n equal to 20, and see what is happening. Okay, you can, you could, that's, it's clever. So, you can take phi naught equal to 0, but then, if I'm just saying keep the phi naught there because it will tell you more generally what is happening. But yes, if you wish, you can begin with the case phi naught equal to 0, right? It would still illustrate what is happening, and then you could later on generalize it to phi naught, any arbitrary phi naught. Fine. So this would be a problem which you will solve and think about. Anyway, can some of you guess what might happen, since some of you have taught this course before? Can some of you venture a guess what might happen in the sum, partial sum? Yes? Okay. See, okay, let me ask you an easier question. What will happen at the points of sampling? Let's first try and guess that. What will happen at the point? That's, in fact, we don't even need to guess. Yes, yeah. Arising at the points of sampling. Okay, yeah. Yes. Okay, yes, that's a good point. Yes. So what happens at the points of, Asha, let me ask you, what is the value of all these sinusoids at the point of sampling? Do they have the same value, different values? What do they have at the points of sampling? No, let's focus on the points of sampling. So what happens at the points of sampling? In fact, let's work it out right now. Yeah, so let me, see, try and recall. Let's do an exercise here, right? So let's do the exercise now in class, since I know it's, it takes, you can discuss, first think yourself and discuss among your partners and tell me what happens here at the points of sampling, right? So now let me give you a couple of minutes, do this. Partial sum, I'm saying partial sum because you can calculate the partial sum in closed form, and also, I mean, the infinite sum you cannot, it may be difficult to evaluate, right? So I'm just saying partial sum because you get a feel of what is happening, and then you can start extrapolating to what will happen as it increases. So I said partial sum because it will be difficult to sense what might happen as n tends to infinity. So first question, now the first question to you is, this is something which you can do right now. Tell me what is the sum at the points of sampling. That means find the sum, find this partial sum. This is more like a tutorial exercise. At t equal to nts. Let's take a couple of minutes and solve it. Some of you should, now first let's do a proper think, pair, share here. Let's first spend some time in trying to solve it ourselves. Now I'll tell you when you can start discussing with your partners. So don't discuss with your partners. Try and solve it on your own. First try and solve it. Find the sum at the points of sampling. Maybe the TAs can go around and help them. Yes. That's right, yes. You must preserve the, yes, so you have to preserve the sign of, so when you take plus here, you must take plus there, you take minus here, you must take minus here, right? And the fundamental, yes. Very good, that's very nice. Would you come and explain? You have something? What is your, you've solved something? Let's see. Yes, please. You can also come. Where did you come? Yes.
I have taken not killer, but same sum.
Okay.
I have done for only 2, n equals 42.
Okay.
So this will come a naught into cos of 1 kilohertz plus cos of 19 kilohertz plus cos of 22. And I have taken pi naught to his.
No, that's okay, yes. Fine, fair enough. Yeah. So what would you get? You get something interesting? Well, you have to, you have not yet calculated that, right? Yeah. Okay, please.
Calculator.
Not calculator. I don't need a calculator. I must be able to sum the sinusoids, right? So I must sum two sinusoids. Maybe you can try doing. Yeah, would you like to show me what you did? Okay, come and that's very good. That's very interesting. I want to come and explain what you've done.
First, we expanded this one.
Yes.
And solved this one.
Okay.
And this always be 1.
Okay.
Yeah, so it is inside summation 1 plus 1, 2. This is 1. This is our n. And this is 1 n plus 1 into this original signal.
Okay, so now explain your answer. Yeah, I think you're on the right track. That's right. So explain your answer.
As for my solution, if we expand this term if we expand, then we will get our closed form equation as a naught cos 2 pi t by ts into cos this one, okay, omega naught t. And here also we have this one, so these two part will be common, so we can take that out, because in one term there is no k, so we can take that out of summation. So that our original signal. So original signal we can take out of summation. Here inside summation, so this part will always be 1, and that is we are summing that for n time, so it will be n, and n plus 1 into our original signal.
Very good. That's very correct. Actually, he's right. So n plus 1, or would it be right? I mean, you're on the right track. Yeah, that's a good idea. Do that. Yes. Well, look at it this way. How did we start discussing these frequencies? How did we start discussing these frequencies in the first place? What was our criterion to write down these expressions? What was our criterion to write down these expressions? We wanted the same samples at the same points. Which points? All points t equal to nts. So I have already told you the answer, isn't it? All these sinusoids have the same samples at the same points. So when I add them, if I make these partial sums, how many sinusoids am I taking? I am taking n, or well, be careful. How many sinusoids am I taking here? As a function of n, how many sinusoids am I taking here? Not n. Because I remember I'm taking the plus sign with the plus sign and minus sign with the minus sign. So for each value of k, how many sinusoids am I taking? Yeah. So in all I'm taking 2n. So 2n times that sample comes from here, and 1 times that sample comes from here. So what happens when I calculate these partial sums at the points of sampling? The value at the point of sampling gets multiplied by 2n plus 1. Is that right? The value at the points of sampling gets multiplied by 2n plus 1. Now the challenge part of the problem is what happens at the other points in time, right? Now so I have given you a hint now how to, so what happens at the other points in time? Let me ask you to venture a guess. Let us see how your intuition works. What do you think happens at the other points in time? Same as what? So which is the original signal? Oh, you're saying that it remains, okay. But what do you think is that partial sum at other? Well, all right. Yeah, anybody else? So one answer I have is that it remains what it is with the original signal. Okay. Yeah. Okay. So you're saying that at the points of sampling you are multiplying by 2n plus 1, but at the other points your view is that it remains what the original sinusoid was. All right. That's, see if that's what happens. Any other views on this? Any other views on this? Remember, you're summing the original sinusoid with 2n other sinusoids, right? What do you think might happen? That's one view. I mean, we don't know right now, right? Well, think about it. So this is an exercise which all of you. So it's an exercise which you do. You can do it group wise, but you will spend. My teaching associates will spend, at least half a session with you in discussing the solution to this problem, right? As a challenge problem. Very good. Now, anyway, what is very clear is that all these sinusoids have the same samples at the same points. And we now also understand that we don't want this confusion that is created, right? What is the confusion created? If you had f naughts, we listed out all the frequencies, right, that have the same samples, the same points. The frequency f naught, the frequency fs minus f naught, the frequency fs plus f naught, the frequency and so on, 2fs minus f naught and so on, 2fs plus f naught and so on and so forth, forever. So where is the confusion first likely to occur? Between these two frequencies, isn't it? And therefore, if f naught is less than fs minus f naught, which means that fs is greater than twice f naught, then clearly fs minus f naught will be greater than, then there will be no confusion. The lowest frequency is indeed the frequency with which you, and of course, fs needs to be greater than twice f naught, and now we can look at the sampling theorem with which we are familiar. You need this to happen for every f naught, for every frequency present in the signal. That means the fs needs to be greater than twice f naught for every f naught that was present in the signal. So which one should we consider the highest of them? Right, it's maximum. But what does it mean? It means that there should be a highest. There should be a highest f naught which we can consider to come up with this criterion. The sampling frequency should be greater than twice of the maximum. So there must be a maximum frequency component. So what are we asking the signal to be? The signal should not have a Fourier transform which is non-zero beyond some frequency. In other words, the signal needs to be band limited. So it's only a band limited signal that can be sampled in such a way that it can be reconstructed by this principle. So the sampling theorem as we know it applies to band limited signals. That means there must be an upper limit on the sinusoidal frequency that is a part of that signal, right? The Fourier transform needs to be 0 after a certain frequency. Otherwise, you can never come out with an f naught. You can never meet this criterion for all the sinusoidal frequencies present in the signal. Now let's take a minute to understand what band limitedness means physically. You see, this is all very interesting mathematically, but physically what is the implication of band limitedness? To understand that, let us understand the implication of having signals with a Fourier transform which is more and more wide band, which means that more and more of the spectrum is occupied. Now, you see, let's take again a sinusoid. So you have the sinusoid, a naught cos omega naught t plus phi. Okay. Let us look at the rate of change of this sinusoid, right? So that's again a sinusoid, of course. So I take the derivative. When you take the derivative of sinusoid, what happens to the amplitude and what happens to the phase? The amplitude is multiplied by the frequency, angular frequency. And of course, there's a 90 degrees change of phase. The 90 degrees change of phase is not such a concern right now, but the amplitude is. So, the higher the sinusoidal frequency is present in the original signal, the faster the signal varies, the more the variation, the more, in some sense it suggests that there is a greater contribution to the derivative of the signal, which means that the signal tends to vary faster and faster. Because when you take the derivative, higher frequencies are multiplied by a higher factor. So the higher the frequency is present in a signal, the more it reflects in the derivative being significant. Is that right? So, in some sense, what is the meaning of band limitedness? What is the meaning of band limitedness physically? Yes, yes, tell me. Yeah, why don't you come and explain? That's a good answer. Yes, come and explain that to the class.
See, as it was told that band limited means it's upper limited is restricting the signal for a highest frequency. Now, differentiation dxt dt, we are finding the amplitude is a naught omega naught. So, in band limiting, if we are restricting the value of omega naught, that time a naught omega naught will also get restricted to a certain value. That means we are putting a bar on the how fast the signal will change. If the signal is very high, it's having very high frequency, then its dynamic response also will become very fast. Like that.
Very correct. That's very correct. That means
It will be very high. Yeah. So yeah, rate of change will be very fast. That means dynamic response will be very fast.
So there's a limit. Yeah, that's very correct. It's very correct. So that's very correct. What Saurabh said is very correct. The band limitedness of a signal essentially says that there's a limit to how fast the signal can change. The limit to how fast the signal can change, right? Now, let us look at this whole principle of sampling from a slightly different perspective. How did we, frame the principle of sampling? We said we begin with a sinusoid and then we'll sample the sinusoid and we'll try and construct all sinusoids which have the same samples, the same points. There's a confusion created. And we said the problem is not that I can't, if I have those samples at those points, it's not that I cannot reconstruct a signal which has those samples at those points. The problem is there are just too many of those signals. So what is the process of reconstruction when you have sample? What is really the process of reconstruction of the samples? It's a problem of eliminating the ambiguity. That's another way of looking at it, right? How do you eliminate that ambiguity? You eliminate that ambiguity by using the knowledge that you have prior. With no prior knowledge, you cannot eliminate the ambiguity. So if I told you that I've sampled a sinusoid and I have these samples at these points, and if I did not tell you that the frequency was as low as it should be, then I have no answer to the question. There can be an infinite number of sinusoids, all of which have the same samples at those points, right? So there is no way to resolve ambiguity without a priori knowledge. So what is sampling and reconstruction at some level? Let's write this down and let's understand this very clearly. Sampling and reconstruction. Sampling means creating ambiguity, creating multiple possibilities from one. So I had an original signal, but because I've sampled, I've created multiple possibilities. There can be several different signals which have the same samples at the same points, right? What is reconstruction from the samples? It is resolving this ambiguity. And how do you resolve the ambiguity? By using a priori knowledge, by using prior information. What is the a priori knowledge that we often assume? The a priori knowledge that we often assume is band limitedness. That means there's an upper limit on the frequencies present. Isn't it? And then what do you do? How do you reconstruct the signal from its samples? When you know it's band limited, you can filter the signal that is, you can filter the sampled signal so that it retains only up to what you know to be the maximum possible frequency. So if you know so what was the a priori? For example, suppose you knew that your signal was band limited to 10 kilohertz. What would you do to reconstruct the signal? Filter it so that all sinusoids whose frequencies are more than 10 kilohertz are eliminated. So you can put a low pass filter and cut it off at 10 kilohertz. Is that right? So cut it off at the maximum frequency, record it. Okay. Now, what does sampling do? Yesterday we said that, you have in the signals and systems in the natural domain, we said we would agree to have the same kind of independent variable at the input and the output. If it's continuous at the input, it must be continuous at the output. If it is discrete at the input, it must be discrete at the output, right? Now, with the advent of sampling, when we have now created the possibility of sampling, we can allow different kinds of variables at the input and output. So, you could begin with a continuous time signal, and when you sample it, it becomes a discrete time signal. You have a discrete time signal, you can reconstruct the continuous time signal from it, right? Which means that now you can deal with systems which are hybrid in their independent variables, right? You could begin with a continuous time system and go to a discrete system, or you could begin with a discrete system and go to a continuous system, right? By the process of sampling and reconstruction, right? So now this is the third module. Yesterday I said that, in the first module on signals and systems, we talk about natural systems and signals in the natural domain. What was the second module? The Fourier transform, and now we have the third module. The third module is sampling and reconstruction. And what is the purpose of this sampling and reconstruction? Being able to create the possibility of hybrid independent variables. Continuous independent variable at the input and discrete independent variable at the output, or vice versa. That's right. So, being able to deal with hybrid independent variables is the purpose of the third module, and of course, the whole science behind it. Now, to illustrate further this idea of a priori knowledge, let us take an extreme situation. Why I am saying this is because we should not think that sampling and reconstruction only requires band limited signals. Suppose I told you, for example, as I said, let's take an extreme situation. Suppose I told you, for example, your signal is a constant, it's a DC voltage. How many samples of the signal would you require to reconstruct a signal perfectly? Only one sample. Is that right? You require only one sample. Because the moment you sample the signal at one point, you know what that DC value is. So you don't need to know anything else. Suppose I have, now this is an exercise which I want you to do right now. It's not difficult, but it's a simple yet illustrative exercise. I have a signal that looks like this. In fact, let me do the following. I tell you that, I took this RC circuit in the morning, right? Now, what I'll do is, I'm looking at the output voltage, isn't it, across the capacitor. Instead, let me look at the current in the capacitor. Yeah, let me look at the current in the capacitor. And I tell you that, firstly, in fact, I want you to find out the current with a unit step input. So we have looked at the step response of this circuit, isn't it? Now, in the step response, I found out the voltage across the capacitor as a function of time when I apply the unit step. But you can also find out the current in the capacitor as a function of time when I apply a unit step, right? Or the current in the resistor, it's the same thing. My question to you is, how many samples do I need to look at how many points in time do I need to look at the current in the capacitor to determine the values of R and C? And how will I find the values of R and C from these two measurements? Or I gave you the answer. At how many points do I need to look at the current in the capacitor to determine the values of R and C? And how do I determine the values of R and C? 2 points. Yeah, how do you come out with the come? Vikash has an answer. He says it requires 2 points. How do you come out with the conclusion that you require 2 points? Yeah.
Yes. We require 2 points because we just need to know the rate of change. If I know 2 points, then I can calculate the rate of change.
Oh, I see. Okay. It's interesting. The rate of change between what?
Because we know that capacitor, so either it will exponentially decay or increase. So that the rate of change, I can know, then I can predict.
But you know that, can you decide beforehand whether it's going to decay, the current is going to decay or the current is going to increase?
Yeah, we can decide that if our the voltage source is there, then
I'm talking about step input.
Yeah, okay. So step input means it will saturate at one point.
What will saturate?
That current through the capacitor. It will become zero.
I don't think I can answer it properly, but
try. It's always good.
Whether the capacitor charge or discharge, current always goes down.
No, but tell me, let's be specific. Okay. I'm applying a unit step here. The capacitor is uncharged.
Yes.
Now my question to you is, what is the nature of the current?
The current will exponentially decay.
Exponentially decay. Very good. Now my next question is, at how many points do I need to observe this current to find out the values of the resistance and capacitance?
Okay. So we had that. What's the equation for current for capacitor? I equals to 1 upon RC minus 1 upon RC dV by dt, right? Yes. E to the power V by T. That's so we will put 2 equations for that. And since we have unit step input, so we will always be 1 and time will vary only. So at that two time sample, we will have the value of time also. So T will be there, and only RC will have to calculate. So we will got the time constant from there, and I think from there we can calculate R and C also. Yeah, we will get.
Maybe you need to tell me whether I framed the question correctly or not, right? Or if the question can be answered.
Tau can be calculated, right?
Yeah, would you like to come and illustrate what you say? Yeah, very good. Yeah, Kash seems to have a problem. Yeah.
So we know that time constant, that rate of change depends upon time constant. So if you know the that 2 point, then we know the difference is the differentiation. So we can determine the rate of change. So tau we know, but by knowing the tau, we cannot determine R and C because 2 unknown variables are there. So either we need to know either C or R to determine other variable.
Well, that's interesting. Okay, let me solve. We remember the expression for the voltage across the capacitor for a unit step. What was the unit step response? 1 minus e to the 1 minus e to the power minus t by tau into ut. Is that right? So what do you notice? Now take the derivative of this. It would be 1 by tau e raised to the power minus t by tau ut. So how many unknowns do I have in this expression? 2. How many unknowns do I have in this expression? So unfortunately I have only one unknown here, isn't it? It's tau. There's only one unknown in this equation. So no matter how many measurements I take, I will only be getting information about one unknown. From that unknown, can I uniquely determine R and C? Yes? Yeah? Does it have two variables? See, I mean, can, if I, okay, yeah, what will you be able to find? See, you know 1 by tau, so of course, you know, if you take t equal to 0, you will be able to find 1 by tau. Now, once you know 1 by tau, of course, you can find tau. Now, once you know tau, is there anything more to find in this expression? So, what does it mean? It means that when I ask a question like this, see, why I gave you this question is you must be careful when framing questions in your examination, right? Now, if I put this question in your examination, how many measurements do I need to make on this current to find the values of R and C? What is the answer? You cannot find, no, not one. You cannot find the values of R and C by making measurements on the current here uniquely. It's not unique. There can be an infinite, but what can you find? The product of R and C, right? You can find tau, but I cannot find the R and C individually. Yeah? Unique solution is not possible, right? Then what is possible? Can I do something, you know, can I find the value of R and C individually in some way?
You have to use the discharge time. Step function is by voltage. Right. So we know that it requires 4 time constants to current is known. So voltage is also known. So that we can find that.
So I'll leave this as a question for you to think about, right? Suppose I want to find R. So the first part is, so you see now this is, you know, now what is the a priori knowledge I have here? The a priori knowledge I have here is, this is the nature of the current. Is that right?
So only one measurement will be enough.
One measurement will be enough. But with one measurement, what do you get?
If we know at t equals to 0 the current.
Yes.
So at t equals to current will be V by R. We know current.
Yes.
We know,
Yes.
R can be W.
Yes.
And then when we know R, from other measurement we know tau. So C can be.
But then, what is the measurement you're making? You're making a measurement.
At t equals to 0.
So I need to control the input. Right? I need to control the input. Otherwise, I cannot independently find R and C, isn't it? How can I? It's already mentioned. It's a step. Right? Okay. Anyway, so take this question. Now, you know, your task, see, this is in a black box. This RC circuit has been put in a black box. Now it's a task, you know, given to you. I want to make external measurements on this black box. I know it's an RC circuit like this. I want to make external measurements on this black box to obtain the values of R and C. What are the different ways in which I can do it?
4 pins.
4 pins, yeah. So I have 4 pins like this. I know, and I also know this is a circuit inside, right? Now my task is, what are the different ways I can employ to find the values of R and C? And of course, the auxiliary question which I asked you just now is, suppose I measured the current in the capacitor, right? Or maybe not even the current in the capacitor. I applied a unit step and I put an ammeter here, an ammeter which can measure the current going in, right? Now, at how many points, if I put a unit step, at how many points do I need to observe that current to write down the full expression for the current? Right? So that's the second question. Take these questions with you and think about them. Right? Take them, think about them. The good thing is that these questions have woken many of you up. Is that right? The questions have definitely woken many of you up. So we shall need to conclude now. It's 6:45, right? And we'll meet again. I shall meet you at 10 a.m. tomorrow. And we'll have 2 sessions tomorrow with me. And then my teaching associates will take over the sessions afterwards. Right?